because never or very few times do you guys ask questions about homework, because after a while you end up getting the correct one. But there are some I feel like I need to go over after the last couple of years of missing the same problem. And so I have the advantage of being able to pull up the most missed questions from you guys, right? So in other words, this carpool B question, 27% of you guys got it right on the first try. And I mean, it's okay, it happens, right? But that, and sometimes you click the wrong one, and a lot of times you get it and you, oh yeah, I got it. But it, again, some of these I feel like I need to go over, okay? So I'm gonna hit this one, carpool one. I don't remember what this one was. Oh, this is, this one is missed a lot. And there's a reason why I need to go over it. You'll see it again, okay? And it's missed a whole lot. Coach Ferguson uses a thermometer to measure temperature in Fahrenheit, 20 different locations. We get a mean of 77 and a standard deviation of 3. Recall that Celsius is equal to 5/9 Fahrenheit minus 1/69. What is the standard deviation of the temperature in Celsius? Remember that standard deviation is not affected by addition or subtraction. So this minus 1/69 you don't use because it's not affected by the subtraction. Okay? So when you're plugging in this 3, you plug in the 3 with the Fahrenheit, you only multiply it by the 5/9 because that's the only thing that affects the spread. Addition and subtraction only affects the center, right? So please remember that, especially on the test. It might be this exact question, I don't remember, but I do remember it's something to do with a Fahrenheit conversion. Okay? Go back. Oops, I didn't want to do that. I thought I could do something different. That's all right. 7th hour. The ones that I really don't like to see, the highly or missed responses, are the ones that start off with MC, because those are like the multiple choice questions like you would see on the exam, right? So let's see this one. Oh, these are, I told you guys, that's hard to do, is to convert a relative cumulative frequency graph into something that's a regular graph, if you will. So it starts off fairly steep, it goes steeper, 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 and then it somewhat levels off. Remember, when it's almost horizontal or when it's not very steep, that means that there's not a lot of data. And the steeper it is, it means that there is a lot of data, right? So there's basically a lot of data, a lot of data, a lot of data, and then we start leveling off with not very much data. So we have a lot of data, and we're going off to not very much data. And so that would have to be a skewed right distribution. Is that the right answer? Does anybody recall? Okay. So, oh, here, they're up here. Okay. Shoes. Now we're starting to get, and that was 40%, 47. We're starting to get half again. Most of these. How many pairs of shoes does a typical boy own? To find out, they surveyed 20 male students. So we have 20 dots up there. They recorded the number of pairs of shoes that they own. Given a dot plot, one of the students recorded 22. That's this guy right here. What is his percentile? And his percentile is that number and everything less. Well, if there's 20 dots up here, there's 2 that are not. And so that must be 18 out of 20. And so we just take 18 and divide it by 20 and figure out what that percent is. Okay? So just a couple of things we want to make sure of. But all classes, the most one that's missed is that minus something on the standard deviation. 0 hour, it was a very similar question, but it asked about the mean and the standard deviation. And everybody got the mean correct because you just plug in the mean, because it does affected by both. But the standard deviation is not affected by addition or subtraction. Okay, y'all good? Here we go. Today. Well, I cannot emphasize this enough, but if you don't get today, this year is going to suck for y'all. It's going to be horrible if you don't get today's lesson. Okay? This is huge. We will do this the entire year. We will do this the entire year. And it's not real hard. And I'll be honest with you, 0B thought it may have been the easiest we've ever done it. I think part of it was I did it a little bit slower, and I emphasized how to do this a little bit more. I will say that AP rules have made it easier. In other words, you don't have to show as much as we used to have to show to do these problems. So we'll kind of go over this a lot today, just making sure that we can, please, like I said, if there's something that you guys need, please, please, please ask, because this is huge. This is huge. So density curves and normal distributions. All right, here we go. 2.1. We'll get 2.2. We'll get 2.2 done today, right? What is it? So Thursday, we got review day 1. Tuesday, review day 2. One of those 2 days we'll go over our last test. And then Thursday, we're going to take a test over this one. Okay, but we kind of have a review day. That's how important these 2 sections are. So if we teach 2 sections, I give you 2 seconds to review. This is huge, okay? So density curves and normal distribution. Let's first talk about a density curve. This is not that big of a deal. In fact, I think you guys somewhat already know all this stuff, right? The density curve is just how it follows the trend. So, and we talked about in one of those sections about shape of a distribution, okay? If you can somewhat follow the distribution, the shape of it, that's the density curve. Sometimes they're not curves, sometimes they're straight lines. So it's a curve that just basically follows the trend. It's a density curve, okay? This can be considered a density curve. I would consider that one uniform, okay? I would consider that uniform, straight across. Okay with that? So density curve doesn't necessarily always have to be a curve, but it's just that, okay? And so a curve that follows the trend of the data, all right? Density curve. This one's a density curve. This one, we call it what? Symmetric unimodal. Okay, with that, we'll learn a little bit more about this one today. But symmetric unimodal, okay? Let me give you some properties about this density curve. Again, it's something that I always just assume is really, really common sense. And you probably think it's that too, but we just want to make sure we know it. The density curve is always above the x-axis. Why? Because if it's below the x-axis, those are negative numbers, and we don't have negative data values in statistics. There's no such thing as a negative data value. Like we don't take data values away, right? I mean, it's just, they accumulate positive. So it's always on or above the x-axis, always, okay? It has the area of 1 underneath it. So we've got a little bit of math going on here, a little bit of geometry. Area, 1. I'm going to tell you why it's 1, because it's 100% of the data, right? I got 2 curves right here. This area is 1 because that's 100% of the data. This area is 1 because that's 100% of the data. So every density curve has an area of 1 underneath it. Always 1. And in the area under the curve, above any interval, we'll call it xy. Under the curve, above an interval. So like this area right here, the area under the curve, above the interval, estimates the proportion of data values in that interval. Shouldn't be that foreign to us, right? If my interval went from here to here, that would be 100%. If it goes from here to here, I don't know, what are we going to guess? 30%, something like that. 30% of the data falls between X and Y. So that's what we talk about when we talk about a density curve. It's some kind of curve that follows the trend of the data. These density curves are always above the x-axis. They can't go below, right? And then the area between 2 values, or the area in an interval up into the curve, That proportion of the entire thing is the proportion of data values between there. Okay, this is nothing you'll really be tested on, but it's just things you somewhat start linking together this class. Okay, is everybody good? Everybody good? All right, so this particular one right here, we're going to call that a uniform distribution. It's going to go straight across. Straight across. This is 2 if you can't read it. This is 5 over here if you can't read it. So 100% of the data values fall between 2 and 5. Journey time in minutes. I don't know what it is. Okay with that? Journey time in minutes. It goes from 2 to 5. This is a density curve. It's a straight line. I got this number over here covered up. This is 2. This is 5. Anybody have any idea what that number is? Not 1. Why 1/3? This distance is 3. Okay with that? If this distance is 3, we know the what about a rectangle. The area of a rectangle is length times width, right? We kind of know, that's why we have to have a little bit of math coming into this course. Well, we know that the area is length times width, and we know that the area underneath that curve has to be 1. So if this is 3, that has to be 1/3. And you got to know that for the test. If the width is 10, the height better be 1/10. If the width is 7, then the height is 1/7. Okay? And so then I can go from like 4 to 5. From 4 to 5, which that distance is 1, and this height is 1/3, and 1 times 1/3 is 1/3, or 33%. So 33% goes between 4 and 5. 66% goes between 2 and 4. 50% goes between, where are we at, 3.25? Yeah, 1.25, 1.5, I don't know. Good enough with all that? You're kind of good? So you need to understand that the height of that is 1/3, and why it's 1/3. And it's 1/3 because the width is 3. And if the width is 3, the height has to be 1/3 because the area underneath it has to be 1. Good enough? Y'all okay with a uniform distribution? We don't deal a whole lot with crazy distributions because we can't do math for crazy distributions. Right? We're in an AP statistics course. We're not in a calc-based statistics course. If you're in a calc-based statistics course, we can find the area of all kinds of things because we can understand integrals and that kind of stuff, integrative calculus. But this, I don't have to. It's just length times width. Yippee? Okay. Describing density curves. Okay, so let's look at this type of density curve right here. This stuff is new. This is not new. I'm sorry. This is not new. You already know this stuff, right? We said what? Unimodal, symmetric. Good. What do we know about the mean and the median? They're about the same, or if they're not about the same, they are the same. Good enough with that? So we already know that, right? The mean and median should be really, really close to the middle of the data, okay? This one is skewed to the right, to the bigger numbers positively. All three of those work. What does that do to the mean or the median? Pulls the mean to the skewness, okay? The mean's going to be bigger. So in this particular one, I got a median right here, and then they're calling the mean right here. They're pretty close together, but that still gets pulled, okay? All right, so all this stuff, that's not new. We've learned that previously. Here's what I do want you to know about this, okay? And this will help you estimate some things. The mean is where these curves, these density curves will balance. So picture, you got a pencil right here, and you're setting that curve on top of this. Where it will balance is where the mean is. Where it will balance. And it makes sense right here because it's going to be right in the middle because you have equal on both sides. As it starts getting skewed, then it's got to move this thing down a little bit to help that heavy side over here, or not really the heavy side, but help the long side over here help balance out the heavy side. Okay? So the mean of a density curve is the point where it would balance. Again, It's something that helps you when you're looking at these things, right? We should know the mean is where we're going to balance it. The median, guys, is going to cut them into two equal halves. You kind of, again, we understand this because of the box and whiskers. We understand this because of the relative cumulative frequencies, right? It puts 50% here. Uh-oh, got to write it with a pencil. It puts 50% on the one side and 50% on the other. It puts 50% on one side and 50% on the other. 50% is a little bit different than where it balances. Now, this one, it's not. It's the same. But this is a little bit different to where it balances. 50% and 50%, this needs to get moved down to help balance it. But the 50% is still on this side of it. Just some things to help you be aware of these shapes. Everybody okay? Anything, nothing really brain challenging, I hope. And none of this is really that big a news. Your test question is the 1/3, right? A uniform distribution. That's, you got to understand that. That's the test question. I think one of the test questions also tells you about density curves and all the properties that the density curves, A, B, C, D, or none. Okay? Or all, or whatever. All right. Now, here we go. Big deal. One particularly important family of density curves are a normal curve. Normal curves, okay? It describes normal distributions. Those are the ones that start low, go high, and go back low. The unimodal symmetric distributions. So rather than call them unimodal symmetric, now we'll just call them somewhat normal. Don't ever just use the word normal by itself. Use a squishy word in front of it. I didn't always say approximately normal. And I'll get into such a habit, and you will too, and it's okay if you want to abbreviate approximately. So don't talk about a normal distribution unless if you know it's 100% normal, meaning exact. Okay? We tend to say approximately normal, just somewhat keep that in your head. If you write approximately normal, you won't be wrong. If you write normal, sometimes you will be. So just think about that when we're talking about it. Y'all okay with a normal distribution? Now, normal distributions come in all shapes. Well, I don't want to really say all shapes, but they all don't look like that. That one's not real great. I didn't realize how bad that was. They can be taller. They can be shorter. But if they're shorter, they have to be wider. And if they're taller, they have to be narrower because what? The area underneath it has to be 1. And so the area has to be the same for every single one of these. So this area has to be 1, then this area has to be 1, and if this one's narrower than this one, it has to be taller. If this one's wider, it has to be shorter. That has to happen if they're all on the same scale. Okay, so that we need to somewhat understand about normal distributions. Every normal distribution is described as symmetric, single peak, bell-shaped. Any normal distribution is completely specified by 2 parameters, a mean and a standard deviation. So every single one of these guys has a mean and it has a standard deviation. And what do we know? Shape, center, spread, right? We got a shape, we got a center. Well, guess what? The center or the mean will be right in the middle. Will be right in the middle. And then they all have a standard deviation or a spread. And we tend to use the standard deviation as the spread. Let's talk about where the spread is as that helps you, right? Those of us that have done calculus. Good afternoon. Okay. Yeah, yeah, that's the only two things that I know of. Okay. Yep, I'll holler back at you if I think something. Whatever. Cool. All right. So they all have a standard deviation. Those of us that have done a little bit of calculus or maybe pre-calculus, this might help you, but even if not, somewhat you can understand this. These curves go concave down. At some point, they switch and go concave up. I'm being a little bit dramatic with it. Up, down. Okay with that? That's where the one standard deviation is. That's where it is. So this is one standard deviation. Okay? If it's narrower, then it's going to be a little bit closer because the standard deviations closer together, there's what? Less variability. Okay? AP really doesn't care, but I think it's important for you guys to at least somewhat recognize that and know it and see it. And I don't know. I just always think it's kind of neat that that's where one standard deviation is. If you don't put it right there and you put it down here, AP doesn't care. If you put it all the way out here, they don't care, but you just don't look like you know what you're talking about. So y'all kind of thought good? And if you put it up here, they really won't care, but it just doesn't look like you know what you're talking about. So just somewhat put them right there in the middle somewhere, okay? When you're talking about the mean should be there and the standard deviation somewhere up there, okay? And that's how we're going to label our graphs. We're going to label them. All right, so here we go. Normal distribution, we got a mean, and we got a standard deviation. Remember now we're talking Greek letters. Sometimes we have Greek letters for the mean. Sometimes we have samples. Samples, population. AP's, I don't want to say they don't care. If you don't know, then they won't care. If you know, then they do care. So if you know it's a population, use this one. If you know it's a sample, use this one. And if you know it's a sample, then it has to be S. And if you know it's a sample, it has to be sigma. Okay? Sub S if you want, or sub X. Good. All right, so here's a picture of one. There's mu, there's the standard deviation. There's mu, there's a standard deviation. Everybody good? Questions? Yep. Cool, that's good. X bar S mu sigma. Happy, happy, joy, joy. Anybody else? I do not want to go too fast. All right, so here we go. Normal distributions are very important to us in statistics. Here are 3 reasons. One of them is going to be bigger than all the others. Normal distributions are throughout the entire world. Many, 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 many things are all normal. Many things are normal, okay? Scores taken on tests, SATs, ACTs, AP, they're normally distributed. They're normally distributed here in Bentonville, Arkansas. I can show you the scores for the last 16 years, and there's more 3s than anything else, and then there's more 4s and 2s and 5s and 1s, or at least. It goes up in normal distributions, okay? Repeated, careful measurements of the same quantity. I'm going to measure the diameter of a tennis ball. Most of the time, it's going to be the exact same diameter, but sometimes it's going to be a little bit bigger and a little bit smaller. However, it's going to be really rare to be quite a bit bigger or quite a bit smaller. And so towards the end, there's not going to be very many of those. As we get closer, there's going to be more and more measurements. Good. Characteristics of biological populations. The lengths of a cricket. The yields of corn. We typically have a majority. And if it's not the majority, it's a little bit higher or a little bit lower. But if it's a lot higher or a lot lower, then that doesn't happen very often. Normal distributions are good approximations to the results of many kind of chance outcomes. The proportion of heads when I flip a coin. When I flip a coin, it should be 50% heads. I don't think I'd be surprised if it was 51 or 49. 52, 48. 90, 10, I'll start getting surprises. Those shouldn't happen. They could. So the chances of it happening are a whole lot lower. Good enough with all that, yay? And then it says many of the inference methods. It should be like all. We're going to deal with normal distributions all year long. I kind of mentioned how important this was. Yellow, okay, good. Normal distributions. They're separated by a mean and a standard deviation, and they're all different. Some of them are narrower, some of them are wider. Some of them are shifted to the right, some of them are shifted to the left. But they all start low, go high, go low. Click. Happy? Are we about ready to do something? Here's the empirical rule. I don't think it's necessary that you actually know this per se, but it's helpful to know this. So here's what the empirical rule says. Here's what the empirical rule says. We have a normal distribution. It has to be a normal distribution. If it's not normal, this thing does not exist. Please remember that. Please remember that. I beg you. This does not exist if it's a uniform distribution. It does not exist if it's a skewed distribution. It only exists in a normal distribution. Okay? And here's what it says. If I go one standard deviation away, that is 68% of the data. That is 68% of the data. One standard deviation to the right and one standard deviation to the left. Okay, that is 68% of the data. Now, that must mean that right here is 34%, and this is 34%. Okay with that? Just kind of help you along a little bit. There are many different normal curves, but they all have the same properties. They all have these properties. And the properties are 68% fall within one standard deviation of the mean. 68% fall within one standard deviation of the mean. So the majority fall within one if it's a normal curve. Picture just like I saw. 95% fall within two. Holy cow. 95% fall within two. Kind of go back to our picture, right? If this is one, well, the same distance has to be two. It's not any shorter, not any longer. Well, by then, guys, I've gotten almost to the end, right? That's 95% within two standard deviations. And then, of course, with the 68, 95, 99, 7, now I'm guessing what? Within three, we got darn near everything. 99.7% is within three standard deviations of the mean. This is called the empirical rule. It only works with normal distributions. If you want to insult someone, I think intelligence level is normally distributed, and you could tell them you're about 6 deviations below the mean. That's pretty mean, because 99.7 are within 3. You're 6. You're pretty stupid. That's mean, right? Don't say that to anybody. Don't be a bully. We talked about that in advisory today. Any questions about that empirical rule? You don't have to have that memorized. It's helpful if you do know it, because a lot of things that AP will do is they'll do it within 1 or 2 or 3 standard deviations. How about this? What do we know if a data value falls outside of 3 standard deviations? You're significantly significant, because it's likely not to happen by chance alone. Man, if you can get that, that's really starting to ha-ha our next semester. Okay, good? Questions? Okay, let's go on. Here's a picture of it, right? Here's 1 standard deviation, here's 2 standard deviations, and there's the 3rd. Okay. I cannot emphasize this enough. I cannot emphasize this enough. Some of you knuckleheads are going to use the empirical rule when it's not normally distributed. It has to be normally distributed or approximately normally distributed. It has to be. It has to be. Okay. All right, we ready? The standard normal distribution. Standard. Let's see, what day is this? Tuesday, Friday. We talked about the standardized score. The standard normal distribution is also called the Z distribution. Okay, we have a Z distribution or a standard distribution. And what that is, guys, is a normal distribution with a mean equal to 0 and a standard deviation equal to 1. That is the standard normal distribution. That is the standard normal distribution. That is the Z distribution. Okay? It used to be used a whole lot. AP's not as stickler about the standard normal curve anymore, but understand that's what the standard normal curve is. Okay? All right. Here's how you're going to find an area of a distribution. Here's how you're going to find an area of a distribution. The very first thing I expect you to do is draw a distribution. Draw it. Do understand that this is only for free response, right? If it's multiple choice, I don't care how you do these. So draw it. Take you a line, draw you a curve, draw it. Label. They're going to tell you what the mean is. They're going to tell you what the standard deviation is. Label it. And I don't care if you label this to the right or to the left, because both of those are the same thing. So draw and label a normal distribution. Draw and label a normal distribution. Label the mean, label the standard deviation, and the area shaded. This will make sense to you in just a second. Okay, this will make sense and more in just a second. So draw the normal distribution, label the mean, label the standard deviation. If you don't do that, you're not getting an E. You're not going to get an E if you don't do that. We're going to perform calculations. Now, this step has changed over the years, okay? So I'm going to show you the easiest way you can get by with it. But you're going to perform calculations by one of three ways. One of three ways. You're going to use a table, which none of you are going to use. You're going to use your calculator, which some of you will use, or you're going to use Desmos, which I think I'm finding out that more will actually want to use Desmos than even your calculator. But I'll show you all three. But that's what you're going to do by performing the calculations. And then, I can't emphasize this enough. Answer the question. A, T, Q. And if you ever see that on your test, that means they asked a question and you didn't answer it. Is there? I better see a yes or a no. Right? My guess is you're going to have some explaining behind it, but if they ask you a question, make sure you answer that question. Okay? These three things we got to have to get us an E. I have no doubt that you guys will be able to do these three things. These are not difficult at all. They're really not. They're really not. And once you get into the pattern of doing them, you'll be okay, I think. All right. We ready? A couple pencils are going. I don't want to go too fast. I want to make sure we got it. Make sure we got it. Beautiful, beautiful, beautiful. Here we go. The distribution of ITB, Iowa Test of Basic Skills, are among Gary Anda's 7th graders is known to be approximately normal. Whoop, I'm going to stop right there. It's known to be approximately normal. Boom. I'm going to do that. Okay, I'm going to do that right there. And it tells me that it has a mean of 6.84. I'm going to draw a line right here. I'm going to put mu equals 6.84. Why did I use mu and not x bar? Because they use mu. And a standard deviation of 1.55. Why did I use sigma? Because they did. They will never mix and match these things. Right? If you know what mu is and you know what sigma is, if you don't know what mu is, you don't know what sigma is. If you know what x bar is, you know what s is. Okay? Is everybody okay with that? So now I've labeled it. I'm good. What proportion, this is their question, what proportion of these 7th graders have vocabulary scores below 6th grade level? Well, this is 6th grade level, or 6.84 grade. Remember, these are 7th graders, so it's close to 7th grade. 6th grade is over here. Don't put 6th grade over there. This is 6.84. 6 is not over here, it's over here. Where? They don't care. Just put it over here somewhere. 6. Really, I'm a little bit off because I know what about the standard deviation. It's 1.55, which is like 1.5. And 1.5 away from 8.4, sorry, from 6.8 is like 5.3. That's one standard deviation. I'm not one standard deviation, but they don't care. Just get it over here somewhere. Okay? And then they want what? The percent that are below. So that's what I want. I'm going to shade that in. I'm going to shade that in. You've gotten enough to get a P right now without doing anything at all. You've gotten enough points to get a P right now. Now, let me show you how they're going to want this answer, or how I want this answer, or at least how you're going to get full marks. What proportion? You're going to write a big P. Big P, that's the probability. Okay? That's the probability. Open up the probability statement. Probability that X is less than 6. Any questions about that probability statement? Poor kid one year never wrote a probability statement, and every time he didn't write a probability statement, I took off a point. Hard-headed. Big P, X less than 6. Where'd I get all that stuff? What proportion? Well, that means I'm going to have an equal sign. What proportion of the 7th graders are below 6th grade level? Below 6th grade level. If you want to put an equal sign here, you really can. They don't care about that, truthfully. Okay, I know I would argue with it. You probably would argue with it. It says below 6. Why would I put an equal sign? But they don't care. Good? Now, you're going to do one of 3 things. You're going to find table A. You're going to use your calculator. You're going to use Desmos. Let me show you table A. In order to use table A, you won't find 6 on table A. This is important to know whether you're going to use the table or not. This is important to know whether you're going to use the table or not. You won't see 6. You have to find the standardized score, or the z-score for 6, because you got to know how many standard deviations 6 is from the mean. So you need to know that whether you use the table or not, you need to know that that's what you have to do sometimes. Okay? Sometimes. So the z-score for 6, we know, is equal to 6 minus 6.84 divided by the 1.55. Okay? And so this, again, this is only if I'm doing it. So I'm going to go to my little calculator. A little calculator here. 6 minus 6.84, enter. Don't hit divide by. 1.55. Negative. Negative. Why negative? Because you're below the mean by almost a half a standard deviation or a little bit more than half, 0.54. Okay, so 6 is 0.54 standard deviations below the mean. We need to put all this together. We need to understand this. We learned that on Friday of last week. Okay, so from what I will do there is I need to go to the table and look up negative 0.54. So let me show you how to do that. Here's the table. Got to open it up. Z table. This is in the front of your notes. Okay, you got a formula sheet. You open it up, there's a formula sheet. Then you got Z tables. You got the negative Z tables, and if you turn the page, you got the positive Z tables. I need the negative Z tables, and I'm going to make this thing a little bit bigger so we can make sure we see it. Okay. Here's negative 3.4. Why do we not go a whole lot smaller than 3.4? Well, 3 standard deviations is 99.7. So we're not going to see a whole lot more than 3. In fact, notice that this says 0.003 and that says 0.002. We're pretty close to 0. But what number do I need? Negative 0.5. And this is 50, 51, 52, 53, 54. 0, 1, 2, 3, 4. 0.2946. 0.2946. 0.2946. Let me walk all through that again. I know that that's slow, but I'm telling you, this number, they could care less about this number than all this other stuff you did. All right? So I drew a picture, normal curve, because they told me it was a normal curve. I labeled the 0.8 or 6.84 and the 1.55 because that's the mean and that's the standard deviation. And then they asked me what percent is lower than 6. So I drew all that stuff. All right. Then I turned 6 into a z-score. Okay? I turned it into a z-score. You have to understand that because multiple choices will turn them into z-scores. They'll turn them into z-scores for you. Free responses won't, so you don't have to do this for a free response unless you're using a table. So then I had to turn 6 into a z-score by finding it was, oh, I didn't put it on here. What was it? 0.54 negative, right? That was the z-score for it. And then I went to the table and looked up negative 0.5 and went over to the 4. And it was 2946. Good enough there. Any questions? Now, free response. If this is free response, I got this nice little calculator. It will do everything for me. Everything. Don't use the stat key. If you go down and to the right, you see vars. And if you hit vars, just above vars, you see DISTR. Distributions. Distributions. Okay? Normal, normal, inverse norm, not normal, not normal, not normal, not normal, normal. Don't ever, ever, ever use normal PDF. You will not use normal PDF for this class whatsoever. If you could delete it, I wish you could, but you can't. But you're not going to use it. Okay? Normal CDF, cumulative density frequency or cumulative display frequency, I don't know. Something to that effect. Good? Hit enter. You have lower? Nobody else have a calculator? Lower bound. Negative infinity. Negative 9. It doesn't matter how many 9s you put, right? Because what do we know? 3 standard deviations away, we got almost all of it. So if somebody punches negative 9 and somebody else punches negative 99 and somebody else punches negative 9999, you're probably not going to see any difference. Okay? And then the upper bound is 6. I want 6 or less. And then below that, this is the mean. What was the mean? 6 point, was it 84? 84. Didn't go. 1.84. And then the standard deviation is 1.55. Beautiful. And we go down and we hit enter and we hit enter, and it gives me that same 0.2939. 2939. Were those the right numbers? Did I do everything right? Say again? Yes, right. It's a little different, right? But I didn't punch anything wrong on this. Okay. So the table gave us a little bit different answer, right? That happens. They don't care. They don't care, right? I got 2939. They got 2946. It's not that far off, and that's okay. They don't care. They don't care. Like I said, they care less about the answer than they do what all you've done. The picture and the labels and the probability statement will almost give you full credit. Almost. You just got to do a little bit extra step to find that, but they could care less about the answer. They want all the other stuff. Question. One more. Desmos. Desmos used to not be able to do this. You can use Desmos on the AP exam. Okay? You can. Dadgummit. I don't have it bookmarked. I had it up. DES. Didn't go D. DES. There it is. Enter. No telling what this is going to show. Okay. Desmos. This is maybe what it looks like when you type it up, right? Open the graphing calculator. Desmos. You don't want a function right here. You're going to hit this little plus button. And under this plus button, you see expression, you see note, you see table, you see inference, you see folder, and you see image. And we're going to go to inference. That's statistics. Okay? And then over here, now it's going to ask me probability distribution, z-test, t-test, z-test, chi-square test. No, we ain't done tests. That's the second semester. So we want the probability distribution. And then it asks me for a normal distribution. If it's not a normal, you can drop down and you have different kinds of distributions. Here's a uniform distribution. There's a t-distribution. None of these others we're going to use yet. So we just want the normal distribution. Down below it, it asks for the mean. So we'll type in the mean. 6.84. 6.84. Tab over, standard deviation, 1.55. Create the distribution. Wow, that's nice. It drew it for me. And it put the center at 6, and it put a standard deviation of 1.55. That's nice. That's stuff I need to put on my paper. Now, over here, here's my normal distribution. Here's my mean standard deviation. Hit cumulative probability, okay? And then it's going to ask you for several things. Inner, outer, left, right. I want the left because it's just less than. I want the area, and I want X when it's less than 6. 6. Notice that my thing jumped. 0.294. It even has the probability statement. Yes, no? Beautiful. They know you're going to use your calculator. They know you're going to use your table. They know you're going to use Desmos. You have to. Nobody knows how to do this stuff without it. You have to use your calculator. That's why we have calculator. We have to. You can't find the area of that curve and the integral from here to here without knowing your calculator. Okay? Any questions? $2,946. Again, This can be a little off depending on how you got your answer. What the calculator gave me, 293 something. This gave me 2946, and Desmos gave me 294. They don't care. Don't make it 3. Don't make it 3. Don't round this up and round this up and round this up to a 3. I think 294 is different than 3. Okay? All right. Beautiful. Let's proceed on. We're close. We're doing good. If you're bored, that means you got it and you don't have to worry about it. Draw a normal distribution, label the mean, label the standard deviation. Perform the calculation, show your work. Be sure to answer the question when asked. So, what proportion of these 7th graders have vocabulary scores? If you don't want to write a probability statement, you can write it out in words. I don't think I want to write all that stuff. We estimate that 29.4 of Gary, Indiana 7th graders' scores fall below the 6th grade level on the ITBS vocabulary test. If it asked me in context, then I got to write all this stuff. But just remember that that's like a free response type versus a multiple choice type. Okay? And if it doesn't say anything about context, you're okay. Click. As noted in the preceding example, studies of automobile safety, this is not the preceding example, suggest that stopping distance follow a normal curve. Boom. As soon as I hear it, I draw it. We're going to do normal curves so much, guys, you're going to miss the one on the test that's not normal. Make sure you read carefully. Okay, if it doesn't say it's normal, you can't make it normal. If it says it's uniform, it's straight across. If it says it's trapezoidal, it won't say that. Okay, it has a mean of 155. So we'll say mean of 155. We'll say a standard deviation of 3. Daniel is driving one of these cars at 62 miles per hour. That's good because this is a distribution for 62 miles an hour. When she spots a wreck at 160 feet in front of her, she needs to make an emergency stop. What percent of the cars, when going 62, will be able to make a stop less than 160? $155, $160. $160. My answer better be bigger than 50%. It better be bigger than 50%. Okay? And then I'm going to write the probability that X will be less than 160. And now I just got to either one of 3 things. Look it up on my calculator, look it up on Desmos, or I got to turn 160 into a z-score. I don't think you want to use the table, but again, I've got to emphasize to you, you need to understand that they might turn that to a z-score on a multiple choice question. And you'll know it because it will say this, right? It will say the probability of, I'm sorry, let me fix that, z being less than. Y'all okay? And if it says the probability that z is less than, they must have changed that into a z-score. Go ahead and talk to me. Say again? By using an inverse formula, yeah. Yep, by going backwards on the formula. Good? Okay, so again, here we go. I'll just do this on my calculator. I almost think the calculator is a little easier, but that's just because I've been using it forever. Second distributions, normal CDF. The mean was, I'm sorry, I want less than, so negative 9999 to 160, 155, 3. 95% of the time, I'm going to be able to make this stop. 5% of the time, I'm going to have a wreck. Make sure you answer the question. It might ask, what percent of the time will she not stop? Okay? Just make sure you understand what the question asks, and you have to take it from there. So my answer will be 95%. So we'll go here, we'll apply this, and we'll put 0.95 right there. Okay? 95%. Again, Desmos, calculator, table. Table, you got to turn it into a z-score. If you decide to look it up on a table, be careful because the table only goes to the left. Follow what I'm saying, right? The table only goes to the left. So let me get a pencil again. Dadgummit. The table only goes to the left. So if I draw a normal curve, right, and I know what this means is, and I want it greater than, you almost can't, I don't want to say you can't use a table, because you can use a table and find this area and subtract it from 1, because you know the area of the whole thing is 1. Yes, no? But your calculator doesn't care. You would just go from this number to 99999. Or Desmos, you will just use greater than instead of less than. Just kind of take all that into account, okay? This mistake can be prevented by drawing it. Because if you draw it, you know about what the percentage should be. That helps. Okay. What percent of Spieth drives are at least 290? At least 290. So we got a normal curve. Again, emphasize it. Normal distribution, okay? Make sure that's on there. We got a mean of 304, a standard deviation of 8. He needs to hit it 290. That's 304. 290 is somewhere over here. Again, guys, they don't really care where you put it. And then I'm going to look up, I'm going to do one of 3 things, right? I'm going to turn this into a z-score, find this area and subtract it from 1. You need to understand all that stuff. You're probably not going to do it. A multiple choice might. So turn that into a z-score, look it up on the table to the left, subtract it from 1. And so it's very possible you might see something like this, 1 minus the probability that z is less than something. Y'all kind of make sense with that? Okay? 1 minus the probability that z is less than whatever that z-score is. Okay? That's why you have to understand what you're doing here, even though most of you won't do that. And I wouldn't either. Right? If I was asked a question, I wouldn't use that. I'd use my calculator or Desmos. Okay? Calculator, here's my mean, here's my standard deviation, here's my minimum this time is 290. My maximum is 99999, positive 999. Okay, if you put it in backwards, it'll give you an error. Okay, all right, last thing I need to show you. Last thing I need to show you. Recognize the difference in this question. When professional golfer Jordan Spieth hits his driver, the distance travels normal distribution with a mean of 304. So same question or same information. Mean of 304, standard deviation of 8. On another golf hole, Spieth has the opportunity to drive the ball onto the green if he hits it between 305 and 325. 305, 325. Good enough with that? What percent of Spieth travel within that interval? So now my lower bound is 305. My upper is 325. Okay? Is he like, now here's where we kind of, sometimes we get an idiot, we don't answer the question. Is he likely to get it on the green? And that becomes down to percentages. Is it statistically significant or not? Likely, unlikely. Remember, our likely is 5% under it. So if we're over 5%, we're likely to do it. Okay? I think he's going to be fairly likely to get there. All right. That was not the one. I got skipped this morning. All right, skip. Last question, and I'll get you on with your homework. According to the CDC, the heights of 3-year-old females are normally distributed. Okay? I told you, if you want to get into the habit of this, you're going to get pretty good at drawing these things. Normally distributed with a mean of 94.5. Standard deviation 4. Now look at this. 75% are taller than what? So this time, this is 50%, 75%. Oops, sorry, I went backwards on that. 75 are taller. No, I was going right. I have to think about it sometimes. 75% are taller than what value? You'll see the difference in this question now, right? Last time we were looking for the percentage. Now I know the percentage. I want to know that value. Okay? So, 2 different ways. We got to look up the 0.75 on a table, which you don't want to do. But if you do, that's going to give me the z-score. Okay? You don't want to do that. We can go to our calculator. Whoops, sorry, here we go, end. Go to my calculator. And this time, second distributions. Don't ever use PDF. I don't want to know the area. This is an inverse norm. Inverse. We're doing the opposite of what we normally do. Area, 0.75 with a mean of, I already forgot. What was it? $94.5 and 4. 94.5 and 4. 94.5 and 4. Now, we're in trouble here. Some of you guys, if you don't have left, right, center, listen to me, if you don't have left, right, center, it only goes left. It only goes left, your calculator. So if it only goes left, you actually need to do 0.25. Okay? But if you have left, right, center, I can do 0.75 and go to the right. .75% are taller than 91.80. Okay? Desmos. Exit. Plus sign. Inference. Probability. Mean. I already forgot again. 94.5. Tab 3, 4, 4. Create distribution. There's my distribution. Go away. There's my distribution. Now, when I click cumulative probability, inner, outer, left, right. Right. This one says area and this one says bounds. Bounds. Type in 0.75 because I know the area, 0.75. And then I can see 91.8. 91.8. Is that what I got last time? Okay. I cannot emphasize to you the importance of this lesson. Of all the lessons we do all year long, this one's a big one. Okay. We're not doing normal probability plots. I hope you can use a density curve to model a distribution. You should be able to identify the relative locations of the mean and the median from a density curve. The mean will balance it. The median will do 50-50. I hope you can use the empirical rule to estimate, but guys, if you can't use the empirical rule, you don't have to. You can do it on a calculator or Desmos just as easy. I hope you can find the proportion of values specified by a normal distribution by using the table or technology. And then I hope you can find the value that corresponds to a given percentile by using table or technology. Good? The best that you can do. If you have questions, make sure you ask. Homework due Thursday. Boom.